Hello, Stats 193 students. It's Ariel. I'm making another video for you. Going over rectangular and uniform distribution. We'll be going over this on Tuesday, but I thought it would be nice to send this video out tonight to give you a little bit of a basis to go off of for tomorrow. Some of the feedback I got from the survey was that you guys were feeling very confused in class, which I definitely understood beforehand. I'm hoping that more of you guys can get to the tutoring hours now that we've kind of reworked them, and we do have an exam coming up soon and an assignment due soon. So I know I sent out an email to you reminding you of that, but I will also mention it in this video that on the 21st of February you do have an assignment due, your second assignment, by 9 p.m. Central Standard Time. And then on the 27th, that Tuesday, both my morning and my afternoon sections do have their first exam. The exam is not going to have random sampling on it, any kind of sampling, as it just takes too much time. So when you're going over stuff for the exam, don't even worry about the sampling because that is not going to be on the exam. We don't expect you guys to spend that much time on one problem. But let's talk about uniform distribution. The only probability test that we're going to go over for uniform distribution is going to be the rectangular distribution. And the rectangular distribution has that table on page 160, and I wanted to go over that because I'm going to be using that to solve the problem, example 6.1 on page 161. So we've got this table, and we have a rectangle here. And what this rectangle means, before I explain anything else, is that everything under this rectangle has an equal probability of happening. And so in problem 6.1, it talks about the train never leaving on time and arrives late with the same probability anywhere in the interval. So we're looking for the wording same probability. Now, I know there are a couple of equations in this chapter if you've read along at all, and I know it can be a little bit confusing. There are a few of them that I am going to bring up, but I will try to break them down pretty well. The main one that I want you to remember that we need to solve these for the probabilities is 1 over b minus a. And those variables are going to be found on the width of our table, actually. B is going to be the highest value for the width, and A is going to be the lowest value for the width. And now we've got to talk about the height of our rectangle as well. This equation is the equation for the height of the rectangle. So I'm going to say 1 over b minus a equals height. Now you're probably thinking, gosh, Ariel, why do I need to know the height and the width of a rectangle? I didn't know this was trigonometry. I didn't know this was geometry. I thought this was statistics. Well, when we take the height times the width, we get the area. And this area is actually going to be our probability. So let's come down here and talk about 3 more equations before we start this problem. These three equations, there's actually two, because one of them's for standard deviation, and we should all know by now that that's just the square root of our variance. But the mean of x is going to be b plus a over 2. I got a new pen for this thing, and I thought I would improve my handwriting, but my computer just doesn't want to pick up on it. I'm sorry if there's some dots intermittently or it takes a little bit to write something down. This equation does look quite a bit different from the last one, the 1 over b minus a. I don't want to confuse you guys by reworking the 1 over b minus a into this equation for the mean. So I'm just going to give it to you straightforward and tell you that this is the equation for the mean. It will be on your exam listed as the mean of x. So you don't need to remember this one. What you do need to remember is the variance of x. And the variance of x is similar. It's going to be b minus a squared all over 12. And like I said, the standard deviation equals the square root of all of that fun stuff up there. And for these problems, the variance is going to have a sign of sigma squared, that little loop-de-loop. And the standard deviation is going to have a sign of sigma. So now let's work through this problem. John observed that the 8 a.m. commuter train he takes to work never arrives on time and arrives late with the same probability anywhere in the interval between 8:05 and 8:20 a.m. So we know that it arrives between 8:05 and 8:20, and that it's never on time. And the reason we know this is going to be rectangular distribution is in the problem it says that the train always arrives late with same probability anywhere in the interval between 8:05 and 8:20. So when it says that it's the same probability, like I mentioned earlier, we know it's going to be rectangular distribution. Very easy to pick out these ones. So problem A wants to know what's the probability of the train arriving before 8 o'clock a.m. This is kind of a trick question. I'm going to show you guys the long way and the short way to do this one. Let's do the long way first because that one's going to be a little bit more fun. So we set up this table and we say, okay, I know that B has to be over here, and I know that A has to be over here, and I know I have to have a height. Well, what are my B and A going to be? It's a little bit harder to discern what to put down for B and A, what my variables are going to be. I know some of you are thinking, okay, it's got to be 8:05 and 8:20, and you're on the right path. It's actually going to be 5 and 20. Because instead of thinking about this as times that the train is arriving, we're thinking about this as how many minutes late is the train. That's why I'm not using the 8:05 or 8:20. So we've established our width. And we know that our height is 1 over b minus a. If b is 20 and a is 5, then 1 over b minus a equals 1 over 20 minus 5 equals 1 over 15. This is going to be the height of my rectangle. Now I said that there's a trick to this one, and it's kind of a trick question for you. It's asking what the probability is that the train is going to arrive on time. Now, I want you to think about it as, okay, 8 o'clock. How late is the train at 8 o'clock? It's 0 minutes late. And is 0 on my table over here? No, it's not between 5 or 20. It's way the heck over here. So the probability is actually going to be 0. Because 0, which is here, does not lie between 5 and 20. It's not in my rectangle. It's not included in my probability of my train being late. The easy way to do this is to look at the wording and say, okay, it's telling me in the question that the train never arrives on time, and it's asking me for the probability that the train will arrive on time. When the problem tells me that the train never arrives on time, I can say that my probability is 0 because they have told me that it never arrives on time. Very definitive wording there. And that's why wording in statistics is so important. It can save you a lot of time. So we're going to come up here and we're going to solve B. And B wants to know, what's the probability that the train's going to arrive between 8:06 a.m. and 8:13 a.m.? So between 8:06 and 8:13. And what we're going to do for this one too is we're going to set up that table, that graph. And we're going to draw our rectangle in. Now, 3 things that I need to know for this. I need to know B, I need to know A, and we're going to talk about the height in a little bit. So, when I'm looking for B and A, I'm going to look up here at the times that they're giving me. They're wanting to know what the probability is of the train arriving between 8:06 and 8:13. Now remember what I said, when we're not thinking about this in terms of exact time, we're thinking about this in terms of how stinking late is this train. So for this one as well, we're going to use only the 6 to represent 6 minutes late, and only the 13 to represent 13 minutes late. And our 13, because it's larger, is going to go here, and our 6 is going to go here. Because this is numerical. This is 0, 1, 2, 3, 4, 5, 6, and it's going to keep on going up to 13, and it's going to keep on going. And my rectangle represents a space in between the train being 6 minutes late and 13 minutes late. So now that we've got the width, and we know that the width is equal to b minus a, or 13 minus 6, it's going to be 7. I'll draw that in here so I know that this, my width, is 7. Now let's talk about the height. I know for the first problem, we said that 1 over b minus a is going to be my height. That's not going to change for this problem. So for this one, and for any of them coming up in the future here, anything pertaining to this question, my height is still going to be 1 over 15. Because for the height, we're not looking at this. We're not looking at what time frame they're asking us about. We're looking at the time frame that we're given in the problem. So in the problem, it says that the train arrives late with the same probability anywhere in the interval between 8:05 and 8:20 a.m. So it's saying that the height, the 1/15th, it's representing the same probability throughout. I know it's a little bit confusing. Just know that this right here, the height is not going to change throughout the problem. And the reason we solved for A first, and we did it the long way, is so that you know how to, in the beginning of the problem, use the information that you're given in the problem to find the height, because we use that to calculate the probability of different widths. So if we're thinking about this in terms of the last video that I made, the width is going to be like the x's. It's going to be interchangeable. I can pull x's out of the equation. I can put x's in the equation. My x's can switch in and out. But my other variables that aren't x have to stay the same throughout the entire problem. Otherwise, it's going to throw off my calculations, and it's going to throw off my probability if we're continuously changing. That's why that 1/15th, that's like our constant in this equation. So now that we have found the width, which was 7, and the height, which is going to stay at 1/15th, we can come down here and we can solve the problem. So when you're thinking about this, think back to what I said earlier, that the width times the height equals the area equals the probability. Or P of X. I'm going to try to get into the habit more of using the P of X. So we're going to plug in our values. We found that the width was 7. So 7 times our height, which didn't change, it was the 1/15th, is going to give us 7/15ths, which we're then going to convert to a decimal, because I don't like working with fractions. It's going to be 0.4667. What this means, this number here, I can convert this to a percentage and say, okay, this is 46.67%. There's a 46.67% chance that the train is going to arrive between 6 and 13 minutes late, or between 8:06 and 8:13. So when then we come back down here. We're going to solve for C. What's the probability that the train arrives after 8:08? So this one's going to take a little bit of thinking outside of the box too. It's saying after 8:08, but I need a B and I need an A, don't I? And it's only giving me 1. Here after 8:08. And I know enough to say that, okay, instead of having that 8:08 hanging out there, I'm just going to change that to 8 minutes late. So we're looking for the probability of the train arriving after 8:08, after 8 minutes late. So by that wording, I know that 8 is going to be my A, because we're looking for the probability that the train is arriving after 8 minutes late. But the one in question is going to be right here. What's my B? And to know this, we have to look back into the problem. And we have to read the wording very carefully again. So John observed that the 8 a.m. commuter train he takes to work never arrives on time and arrives late with the same probability anywhere in the interval between 8:05 and 8:20 a.m. Because it has the same probability between 8:05 and 8:20, the latest I can go and actually find the probability for this problem is 8:20 a.m. because that's the end of my rectangle. That's the latest my rectangle can go, is 8:20. So I'm going to write 8:20 over here. Going to convert it and say 20 minutes late. And I can put 20 here and say 20 is my B, because 20 is the latest time in my rectangle here. Now what I can do is take my 20 minus 8, I get 12. My width is going to be 12. And you remember what I said about the height, that the height has to stay the same throughout the problem, no matter how many x's we're changing out, or in this case, the a's and the b's that we're changing out. The height equals 1/15, the same as the last two that we've done, because the 1/15 encompasses the entire set from 5 minutes late to 20 minutes late, because the problem says that the same probability only applies, the same probability rule only applies between 5 minutes late and 20 minutes late. So that's why we've got to stick with the same height. We're going to come down here and we're going to solve it. We're going to say, okay, width times height equals area equals the probability of x happening. So my width I found to be 12 times my height, which I found to be 1/15, is going to give me 12/15, and we're definitely converting that one to a decimal. It converts really nicely to 0.8. So when you're looking at this, you can say, okay, I'm going to change this to a percentage, say 80%. There's an 80% chance that that train is going to be somewhere between 8 minutes late and 20 minutes late, which is a lot higher than our last one, but there's definitely more area to the width. And that's kind of a trend that we're going to see with these. Now we'll solve for D. Obtain the mean, the variance, and the standard deviation for the value of late arrival times on the train. This one is going to be a lot easier. It's more of a plug and chug question than a conceptual question where we actually need to read the problem and work the problem and find different variables. So what we're going to do for this one is we're going to go back and we're going to look at the equations again. And I hope that I can find them on this thing. And we went down from here. There they are. So we know that the mean is b plus a over 2. The variance is b minus a squared over 12, and the standard deviation is the square root of that. All I'm going to do is I'm going to apply that to the problem. And because they're not giving me any specific data to find it for, we're just going to use the information given to us in the problem. So for the mean, we know b plus a, no, not 9. B plus a over 2 equals our mu. For our mean. So I can just plug in what I'm given in the problem. And in our first problem that we did, part A, we found our B to be 20 minutes late, or the latest time. And our A, we found to be 5 minutes late, the earliest time that the train, the probability is the same for the train arriving. So let's just plug those in. Let's say, okay, 20 for B plus 5 for A divided by 2. And what does that give us? It gives us 12.5 minutes. But right now, we're in units of being late. So this is going to be 20 minutes late. You guys are never going to want to be late again after this problem, because I feel like I'm saying minutes late all the stinking time. And I apologize. And 5 minutes late. So because we're in units of minutes late, we want to convert back to a regular time. So what I'm going to do is I'm going to say, okay, 8 o'clock a.m. is on time. And I'm going to add 12.5 minutes. And I'm going to get 8, 12, and 30 seconds. a half of a minute is 30 seconds. We're 12 minutes past 8 o'clock, and we're starting at 8. We just found the mean. Go team. So now we're going to find the variance. And the equation tells us for sigma squared, we're going to take our B minus our A, we're going to square it, and we're going to take it all over 12. So now let's plug in our values, and our values don't change from the last problem. We know our B is 20, we know our A is 5, so we're just taking 20 minus 5, square it over 12. And what these parentheses mean, I know order of operations is sometimes funky with you guys on exams, and that's where I see most issues. We're going to take the 20 minus 5 first, and then we're going to square it. So we get 15 from 20 minus 5, and then we're going to square 15 last. And then we'll take the whole thing divided by 12. And what that gives us, after we're done doing our calculations, is 18.75. Now the easy part, for everything that we ever do, sigma is the square root of sigma squared, our variance. So I can say that that is equal to the square root of 18.75, and I'm running out of room over here, so I'm going to carry it up here. Equals 4.3301. And that's it for that problem. I know that this, especially the rectangular distribution, students seem to struggle with the most, just because it's a very different way of thinking about these problems, and the one that we did with time was a little bit more difficult than any other one in the book, which I think is good. I will be making another video with another one of these problems. I do want to send this one out to you tonight though. If you do have any questions, you can feel free to stop in during tutoring hours. I did send out that new tutoring schedule. If you have any other questions about tutoring, you can email me, or any questions about class structure or the assignment, you can definitely feel free to email Professor Onya. Thanks guys, and have a great night.